Well, good day, everyone. Thank you for joining us for this Che Alaska call. I'm joined by a very special guest, Dr. Alissa Cordner from Whitman College, where she is an associate professor of sociology and also co-director of the PFAS Project Lab. Now, this webinar is brought to you by Che Alaska. It's a program of Alaska Community Action on Toxics. We're environmental justice nonprofit based in Anchorage, and today is all about PFAS. Now, before we get started, I do want to say that Che is a international partnership of over 5,000 individuals across 87 countries and all of the 50 states to address environmental justice and health impacts. And they're also a national chapter. So we'll have all the relevant links as well for you guys to follow up and receive some other really cool environmental justice news. And also, before we get started, I will say that ACAT was just in the Capitol in Juneau, Alaska, fighting for Senate Bill 67, which would effectively phase out PFAS from firefighting foams, which is the primary source of PFAS contamination in water in Alaska. We feel that SB 67 is not strong enough, however, and it needs protective amendments. And it was really good timing as well, just because the EPA wants to enact PFAS drinking water regulations. So without further ado, I'll go ahead and pass it over to our guest, Dr. Cordner, to talk about the PFAS Project Lab.
Great. Thank you so much, Adam. It's nice to be here today. As you said, my name is Alissa Cordner. I'm an associate professor at Whitman College, and I'm the co-director of the PFAS Project Lab. I do want to start by saying that Whitman is on the unceded territory of the Confederated Tribes of the Umatilla Indian Reservation, which includes the Walla Walla, Cayuse, and Umatilla people who continue to practice their life ways here today. I'm going to talk today about the PFAS Project Lab, which is an interdisciplinary research organization based mostly at Northeastern. And our goal is, I'm going to share my screen first of all. Our overall mission is to do accessible, high quality, rigorous work on PFAS, on per and polyfluoroalkyl substances, the chemicals that we're here to talk about today. And one of our main goals is just perfectly in alignment with the talk that Adam introduced, the idea of making the invisible visible. So one of the main challenges around PFAS is that they truly are ubiquitous, and they are in all of our bodies. They're in every sample of wildlife that has been tested. They're in drinking water and surface water and groundwater globally, and yet it's very challenging to know where they are and what the impacts might be. So the PFAS Project Lab, we've been working on PFAS. I've been working on PFAS with my co-director, Dr. Brown, since 2014, and we have a really wonderful collaborative group of students, undergraduate students, graduate students, postdocs, and affiliated faculty and independent scientists. And we maintain a website, pfasproject.com, that has a lot of resources, including our PFAS contamination site and community resources map. So just wanted to put that out there right at the beginning. We also have a newsletter. The issue, our March issue, just went out this morning. So if you don't already subscribe, you can subscribe directly on our website, and you can also find all of the previous issues of our newsletter. Before I talk a little bit more about the work that our lab does, I'll give a very brief overview of PFAS, knowing that they are familiar to likely many of you on the webinar today, but they also might be a relatively new topic for others. So PFAS are a really wide class of chemicals that are characterized by an extremely persistent fluorine-carbon bond in their chemical structure. They're a large class of chemicals. I probably should have updated the slide to say that there are over 14,000, and the number of PFAS is debated based on how you define the sort of chemical structure of chemicals in this class. But the list that we've been going off of for a while on the EPA's website now is over 14,000 chemicals in this class. They are extremely persistent in the human body and in all kinds of environmental media. we're exposed to them through a huge range of exposure pathways as well, from including drinking water, food, but also possibly airborne emissions and even dermal exposure. And this means that not only are they ubiquitous around us, but they are also ubiquitous in the human bodies. So studies of PFAS contamination in the human body that are representative of the population find detectable levels of PFAS in close to 100% and over 99% of people who are included in those studies. There are many different exposure routes and possible many different uses of PFAS, including many types of consumer products that we come into contact with every day, ranging from the sort of well-known uses of nonstick cookware and waterproof clothing to things like cosmetics, personal care products, and most recently, very relevant for all of us, COVID-19 testing equipment and personal protective equipment. They're also used in many industrial uses, both as an industrial product, but also as a way to make other industrial processes go more smoothly. I've been working on an issue of PFAS, measurable PFAS in artificial turf. And even if PFAS aren't intentionally added to the turf, it appears that contamination is ubiquitous because PFAS are used to help extrude those little tiny blades of fake grass, those plastic blades of grass. They also, and as Adam mentioned, are a real concern in terms of certain types of firefighting foam. So Class B firefighting foams are used to extinguish fuel-based fires. So imagine an oil or gas fire where you don't want to spray water on it, you spray foam. But Class B foams in the US and in most places around the world have a de facto requirement to be fluorinated. That may be changing with some changing specifications coming out of the Department of Defense, but for decades, Class B firefighting foam, which is the foam that's used at airports, at oil refineries, et cetera, has been fluorinated. And so you have many known contamination sites linked to Class B firefighting foam, or AFFF, the aqueous film forming foam. There are oh, I skipped the slide. There we go. This is a nice visualization of different exposure routes and the ways that PFAS can move through the environment, including movement through the air, movement through the water, how it progresses through the waste stream and ends up in landfills, and then how that can lead back to human exposure. And I'll say as well, I'm happy to share a PDF of the slides with Adam if you have a website or anything to put the slides up, and then also can share it with folks directly. So what does this mean in terms of people's exposure? As I said, almost everybody has measurable levels of PFAS in their bodies. And additionally, research has tried to estimate what proportion of folks are receiving PFAS contaminated drinking water through their public water systems. This, of course, doesn't account for the roughly 1 in 7 people, at least in the US, who are on private wells. I wouldn't be surprised if it's a higher proportion in Alaska, although I don't know the state-by-state breakdown in terms of the number of folks on private drinking water wells. Across the US, though, there's an estimated more than 200 million residents who are receiving PFAS contaminated drinking water. And this matters a lot in terms of those regulations at the federal level that Adam mentioned a moment ago. Additionally, if you look at contamination in different environmental sampling, you find PFAS in freshwater fish, sometimes at extremely concerning levels. The dark orange, this is from a study that was it compiled existing US government data into a publication led by the Environmental Working Group. And you can see that there are samples of with freshwater fish with over 50,000 nanograms per kilogram PFAS levels. There also is ubiquitous contamination of wildlife species. So this is another study that the EWG did, where they pulled existing studies of wildlife samples. I just pulled out the ones that are in Alaska showing contamination of multiple, both marine species and also terrestrial species. So we're all exposed to PFAS. They're in our drinking water. Why does this matter? Well, this matters because PFAS are linked to a range of health effects, including high cholesterol, ulcerative colitis, multiple types of cancer, reproductive and developmental outcomes, thyroid outcomes, immunotoxicity, and additional health endpoints in animal studies. There's a really substantial body of research here, and the human health effects for the PFAS that have been the subject of a lot of research, those health effects, I would say, are pretty undeniable. And there is a very strong call to treat PFAS as a chemical class, not just to look at one chemical at a time, but rather because these chemicals share similar chemical structures and because they target similar organ systems, we should be understanding them scientifically as a chemical class, and we should be regulating them and restricting their use as a chemical class. And so in terms of regulation and monitoring, there have been a couple major proposals at the federal level, including designations of two PFAS, PFOA and PFOS, as hazardous substances under the Comprehensive Environmental Response Comprehension and Liability Act, also known as the Superfund Act. In the absence, up until this point, of federal drinking water standards, a number of states have proposed and enacted regulatory standards. The map here focuses in on the Northeast because these are the places that have had regulatory levels in place, not just a guideline or a screening level, but actually a level that requires testing and then remediation of groundwater, of drinking water, excuse me. And then just a couple of weeks ago, we did have the announcement from the US EPA that identified maximum contaminant levels for 6 PFAS, standalone maximum contaminant levels, or MCLs, for 2 PFAS, PFOA and PFOS, and then this hazard index approach, which basically identifies 4 compounds, PFNA, PFHXS, PFBS, and the GenX compounds, and groups them together so that if a combination of any of these exceeds the hazard index, then that would also be subject to screening and then remediation. So this is certainly an important first step, and it continues to speak to the need for more class-based and inclusive action on PFAS. So one of the major areas of focus for our lab group has been trying to deal with the mismatch between what we know about measured PFAS data on the one hand, and what we think is going on in terms of where that contamination might be, but where testing just hasn't yet been conducted. PFAS testing is expensive, it is resource intensive, it takes time, it takes a lot of money. And so there are many places across the country where contamination is likely, and it has not yet been identified. And we know this is the case because if you look at I should have pulled up a map, I can do that later on in the talk. If you look at the known contamination site database we maintain, which is the only publicly available database of all known sources of PFAS contamination across the country, you see places like New Hampshire or Minnesota and Michigan that seem to have a disproportionate amount of PFAS contamination. Well, it's just because those states have done a whole lot of testing. And what we know to be the case with PFAS is if you test for it, you find it. So what should we do in the places that haven't done a lot of testing? Well, we developed this model that we called the presumptive PFAS contamination model, which basically said if you know some things about where contamination is likely, then you can figure out the types of locations around the country where, or this could be expanded even internationally, where contamination is likely to occur. And we argued that in the absence of high quality testing data, contamination should be assumed at sites where fluorinated firefighting foam has been used either through testing and training or through actual fire responses. It should also be assumed at certain types of industrial facilities based on their known use of PFAS. And it should be assumed as well at sites related to PFAS containing waste. And this could be wastewater treatment plants, could be landfills, could be incinerators. Then what we did was we tried to gather as much publicly available data as possible to identify point locations for these types of facilities. And this led us to our presumptive contamination map. This is available at our website. And we were able to map over 57,000 sites of contamination across the US. This model has since been taken up by a team of journalists and scientists in the European Union to map PFAS contamination sites and presumptive sites as well in the European Union. And that's a really incredible mapping effort. I can put a link in the chat later on. So the last piece of our lab's work that I wanted to talk about with you all today is about a paper that came out in Environmental Health Perspectives at the very end of 2022. This is the journal that's published by the National Institute of Environmental Health Science, and you can see all the co-authors up here. You can see the funding sources, and the paper asked, what's going on with federal PFAS testing efforts in terms of whether those efforts are inclusive of tribal drinking water systems. We know that there are systemic environmental health disparities for residents of tribal nations across the United States, that these communities are disproportionately burdened by different diseases. They experience lower life expectancy compared to non-native communities. But research on drinking water on in tribal communities is limited. There is existing documentation, certainly of sort of case studies of real challenges in accessing safe and accessible drinking water. There also is research looking at how tribal drinking water is more likely to have high levels of inorganic contaminants, nitrates, foul odor, and foul taste. And so what we did was we looked at two existing two federal testing efforts for PFAS, one that had been completed and one that is actually going to start this year. So we looked at the unregulated contaminant monitoring rule. The third round took place in 2013 to 2015, and then the fifth round is going to start up this year and run for the next 2 years. UCMR4, you might wonder what's going on with UCMR4. It didn't actually include any PFAS. So this is a UCMR testing program is through the Safe Drinking Water Act, and it requires EPA to identify contaminants of concern that are not the subject of federal safe drinking water regulation, and to test for them to see if there is population level exposure. So they tested for certain PFAS for 6 of them in 2013 to 2015. They'll test for 29 of them in 2023 to 25. And we compared drinking water systems, public drinking water systems in the US with a tribal owner type. So it's designated in CIDWIS, the Safe Drinking Water Information System, as a Native American owner type versus public drinking water systems that did not have a Native American owner type. And we compared how these systems were included or excluded from UCMR3 and plans for UCMR5. Additionally, we conducted interviews with EPA representatives in all of the regions where there are tribal drinking water systems and EPA headquarters. And we found that tribal drinking water systems were disproportionately excluded from both testing efforts. So here you can see sampling that was undertaken for UCMR3. You can see that about 3% of the tribal systems, I should say, you can see that only 3% of tribal systems were included in UCMR3 compared to about 7% of non-tribal systems. And then you can see that this included about 28% of the population served by tribal drinking water systems compared to 80%, almost 80% of the population served by non-tribal systems. This is because if you look at the row right above the one that I've highlighted, the vast majority, 97.9% of tribal drinking water systems serve fewer than 10,000 people. And this is the sampling criteria for UCMR3, was fewer than 10,000 people. Whereas there are more large drinking water systems that have a non-tribal owner. So this is a really significant exclusion, we argued. And then we said, okay, so what's going to happen with the plans for UCMR 5, excuse me. One of the big changes there is that they are lowering that population threshold. So whereas in UCMR 3, they sampled all large systems serving more than 10,000 people and then a sample of smaller systems, in UCMR 5, they're sampling all systems with more than 3,300 people. So they are really trying to target, they're including then all of those systems between 3,300 people and 10,000 people. So this is a real effort to be more inclusive. But what does this mean? Unfortunately, we still see a disproportionate exclusion of the population served by tribal systems. So about 65%, close to 2/3 of the population served by tribal drinking water systems will have their water tested in UCMR 5, but over 90% of the population served by non-tribal drinking water systems will have their water sampled. So this remains a significant exclusion of the population served by tribal systems. We also then reported results of the interviews we conducted with EPA representatives. Per these conversations, 6 of the 10 regions planned to conduct some voluntary sampling of tribal drinking water systems in 2021 and 2022. There was some funding available from the federal government, so this wasn't testing that tribal communities had to pay for, but it wasn't opt-in, it was all voluntary. And EPA representatives identified many limiting factors or barriers to participating in these testing processes, including the need for testing of other contaminants of concern. You know, we're obviously talking about PFAS, and there are other environmental health priorities for tribal communities. There also are limits in terms of other resources, whether that is time or whether that is the expertise of staff members. There also is an absence of clear guidance from the federal government about what tribal communities should do if higher levels of PFAS would be detected. And there's insufficient funding available for remediation. Representatives also pointed to a lack of EPA certified labs and this need to divide resources across scarce resources, across multiple priority contaminants. So out of the planned testing initiatives in 6 regions, 2 regions, Region 7 and Region 8, have started to report results. Alaska's in Region 10, so no results. We don't even know if there are any planned testing out of any communities in Alaska yet. And at this point, all of the results that are available, at least the last time I checked their database, were below the levels of detection, which is really, that's great news. So that means that the places where they have sampled for PFAS in tribal communities, they haven't been detecting PFAS. So that's certainly good news. But thinking back to our quantitative results, it certainly shows the need for more attention to tribal drinking water concerns. And of course, we're talking here only about the water that people receive from municipally provided public drinking water systems, which does not cover all residents or all tribal members. The takeaway point from this analysis is that even systematic research that is not designed to be biased can still be inequitable. It can still fail to equitably include populations if those populations are disadvantaged in other ways. And we argued that comprehensive PFAS testing for tribal communities is urgently needed. We, of course, hoped after this paper was released that there would be a follow-up announcement from EPA saying they would oversample tribal communities in UCMR 5, and we have not heard that, unfortunately, but hopefully there will be other funding and additional resources available to really get a better understanding of what contamination might look like for tribal communities. We've also been working with the Tribal PFAS Working Group, which is a network of folks who are affiliated with tribal communities and with EPA in some way, and have been working with them on things like concerns about unauthorized dumping and illegal landfills, concerns about the communication and framing around fish consumption or marine food consumption. And so that's a collaboration that we have ongoing. And I'll also say that our piece in environmental health perspectives had an invited it's called an invited perspective along with it. And I've just put the link up here. And this focused in on the water justice issues experienced on the Navajo Nation, and did a lovely job of describing the different water justice issues currently faced. In terms of next steps for this part of our work, we are taking our known and presumptive PFAS contamination maps, and I've put a little screenshot up there, and trying to understand proximity to tribal communities across the US. So one of our postdocs, Dr. Kim Garrett, is working on a spatial analysis of tribal lands and PFAS contamination. And we also have taken surface water samples in collaboration with 4 tribal communities across the country, and those samples are being processed by Dr. Fernandez's lab at Northeastern. I'll finish up just by talking about the additional range of projects that our research group has ongoing. So we continue to maintain our PFAS sites and community resources map. And if you ever learn about a PFAS contamination site that isn't in our database, we would love to include it. You can always email me with information, or our email address is just pfasproject@gmail.com. We also have several projects, including our focus on tribal communities that are looking at environmental justice outcomes related to PFAS. So for example, we can use drinking water boundaries to understand the communities served by drinking water systems with higher versus lower levels of PFAS contamination, and look for differences along lines of race and ethnicity, immigration status, and socioeconomic status. We have a large collaboration with folks at Silent Spring Institute and Michigan State University looking at PFAS and immune function. And a big part of that project is preparing and disseminating materials that are useful to health professionals. So for example, if you know that you're drinking water that has PFAS contamination and you want to talk to your doctor about that contamination, or you're just concerned about PFAS in general, if you go to either our website or the PFAS Exchange website, you can find links to specific fact sheets that have been prepared with clinicians, so with physicians and people working in the medical field, about how, what PFAS are, and then how do you talk to your doctor about PFAS. There's also information about blood testing. So if blood testing is of interest to you and your healthcare provider, things like how do healthcare providers order it? What should you know about insurance, that kind of thing. So that's all available on our website. We also have some projects that are more sort of traditionally in the social science realm of things. So I'm an environmental sociologist by training. And so we have projects looking at the history of PFAS advertising and the way that cultural framings around patriotism and gender and the Cold War are caught up in PFAS. We have a project working on the social costs of PFAS. So thinking not just about, oh, how expensive is drinking water remediation? It is very expensive. But if you compare it to the annual health costs or the impacts on mental health and stress, if we think really broadly about the externalized costs of PFAS contamination, then remediation becomes a much smaller piece of that story. We also have research that studies PFAS advocacy and activism, trying to understand how PFAS has become such a large focus for environmental health activists, and what makes activism or advocacy different in different places, what makes it perhaps have different outcomes or different targets in different places. We also are looking a lot at PFAS governance issues, so trying to understand how PFAS are regulated and legislated at the state, national, and international scales, and how action at those different scales interacts with each other, including things like the idea of regrettable substitution. So if we stop using one PFAS and we start using another one that's very similar to it, we can think about that as a regrettable substitution. But maybe instead of thinking just about, moving from one chemical to the next, how can we think about broader chemical class issues and larger entanglements of not just sort of chemical engineering, but regulatory issues and the connection between regulation and industry. I want to finish up just by acknowledging the wonderful collaborators we have in our PFAS project lab, all of the other faculty and researchers, the postdocs, current students, and then collaborating organizations. And up here we have our website, our Twitter handle, where you can sign up for our newsletter. My email is up there as well. And I think that we have lots of time for questions. So very happy to have questions, or if there's room for more of a dialogue. So thank you very much.
Well, Dr. Cordner, thank you so much for sharing that presentation with us. I mean, it's great. It seems like a really accessible research lab that's super collaborative, which I love. I feel like there is kind of a digital divide, you know, as far as access to information. So just making that is super important. And yeah, I do want to get into the Q&A portion of our webinar, but before we do that, I know that you recently published a paper talking about environmental health activism and how that's dependent on relationship of scientific evidence and the demand for specific types of knowledge. We know that there's been a huge boom in PFAS literature. I was wondering if you could maybe speak about that paper a little bit and what that research found.
Sure, of course. So this is the paper that has been in the works for a while, and it was just published in a social movements journal. Dr. Jenny O'Hayan is the lead author, and I can find the DOI and put it in the chat at some point, or if people want a copy of it, or maybe Adam, you have it. If people want a copy, I'm happy to send it to you if you don't have access to it. So basically, this paper tried to understand the ways that activists engage with science. We know that the PFAS advocacy world is extremely literate and proficient and understands the science around PFAS at a very high level, which is truly extraordinary given how complex this chemical class is, how many different scientific fields are involved in understanding the work that goes into PFAS science. And so we did interviews with PFAS activists and advocates from around the country and tried to understand, well, what we ended up arguing in the paper is that the PFAS advocacy world is certainly using science and leveraging science, but it also is engaging what we call scientific opportunities to change the field of scientific knowledge, to change knowledge production, whether that is through directly suggesting research topics, whether it is through direct participation in research projects, whether it is through directly influencing the funding mechanisms that then fund academic research, that folks who are not scientists themselves, not trained as scientists, not working as scientists, that they truly are acting as people influencing the world of PFAS research in a way that is, I think, really exciting. And we certainly are seeing this in the PFAS realm, but I'm sure it's not unique to PFAS, that climate activists are pushing the climate science in new and important directions. That folks who are working on plastics issues have been pushing that area of research as well. So that's one of our, that's a paper that has just come out that we're really excited about.
Yeah, that's great. And we do have some questions here. Tamila asks, if residents want to filter their water, should they use reverse osmosis or granulated carbon? If reverse osmosis has a mineral additive, would that make it safer? Put you on the spot here.
Right. And I will say, this is not my research area of expertise. However, there is a paper that I will try to call up at this particular moment that I think does a really nice job of answering this question. Let me see if I can, and if I can't find the specific paper, I can, if I can try and connect with you afterwards, that basically looks at point of use, so at the home water filtration, to identify which types of filtration is effective in the home environment. And I just don't want to misspeak, so I do want to try to find this particular paper.
Sure.
I know that I just sent this link to someone quite recently, so
Yeah. Why are you looking for it? I do want to speak a little
Yes.
bit about just investigation of water systems, tribal system, like water systems in Alaska specifically. The DEC has identified over 469 contaminated, like PFAS contaminated sites in Alaska. However, there's just not a lot of movement, and they always default on, well, the EPA hasn't done anything, right? But that shouldn't matter. We know that 23 states across the lower 48 have enacted over 100 PFAS policy, so there should not be any delay, which is why ACAT, a big portion of our work, is dedicated to going to indigenous communities and testing the water for PFAS in animals and wildlife. We know that PFAS bioaccumulates thousands of times within these animals. So subsistence aquatic life is really having those PFAS contaminated that are super toxic, they bioaccumulate, and then subsistence foods that indigenous people eat gets into their body. However, a lot of people, and we always kind of say the same thing, is we don't want to challenge anybody's cultural identity by telling them not to eat it. However, it is super important that they know what's in there. And we have over 229 tribes in Alaska alone. So it's very confusing and just kind of sad that the DEC hasn't done anything yet. So they can't really default on that answer of the EPA not enacting anything, because just last week, they want to start enforcing PFAS water quality standards, which is great. We do have a couple more questions here, if that's okay with you.
Yes, and I did find the article link, and I think I sent it to you, Adam. So I don't know if you can share it more broadly.
I do, yeah. I got it.
That is called Assessing the Effectiveness of Point of Use Residential Drinking Water Filters for PFAS, Nicholas Herkert et al. And basically what this article, what this research group did was they measured PFAS levels after home water filtration. And they find, this is quoting, all under sink dual stage and reverse osmosis filters tested showed near complete removal for all PFAS evaluated. Other filters were more variable. And in particular, they found that whole house activated carbon point of entry systems were variable and sometimes increased the PFAS levels, because if you don't change those filters regularly, the filters are absorbing that PFAS out of the water. And when the filters have too much PFAS, they will actually start sending the PFAS back into the delivered drinking water. And so whole house activated carbon systems did not show effectiveness at PFAS removal. Under the sink, multi-stage carbon filters did show effectiveness, as did under the sink RO filters.
Wow.
But this article is helpful. Yeah, and
go ahead.
It's also discouraging because I know in some communities, the drinking water filtration system being offered by the responsible party is a point of entry carbon filtration system. And so communities might want to use this study to push back on that if that's what's being offered to them.
That's a great resource, and thank you for finding that. I really appreciate it, Dr. Cordner. We do have a couple more questions here. This is from an anonymous attendee. Here on Cape Cod, we have a lot of data on PFAS levels in water, but more limited on airborne levels and levels in food items. Mm-hmm. Are exposure routes for potential negative health outcomes, breast cancer rates and other endocrine disrupting disorders, I think is what they're referring to there, as far as airborne PFAS particles?
So there is a lot of uncertainty about airborne emissions, and I'll also say dermal exposure as well. These are exposure pathways that are not well characterized for PFAS, and the links between potential exposure from airborne or dermal exposure and then health effects is also not well studied. The issue of food contamination is substantial, and is one reason why, if you look at the risk assessment methods behind drinking water advisory levels, they're typically based on what's called an RSC, a relative source contribution of 20%. Most of them are, not all of them, but most of them are, including, I believe, the EPA's recent assessments. And that means that these assessments are assuming that we're getting about 20% of our PFAS contamination every day from drinking water, which means that maybe we're getting up to 80% from some other source, including food, or potentially, although there's a lot of uncertainty, things like airborne emissions. You mentioned the issue of fish consumption, and we know that freshwater fish species have not always, but many of them have high levels of PFAS contamination. And so it is certainly important to think about drinking water as a major contamination source for some communities, but also to be thinking about where other contamination might be in people's daily lives. And food is especially something that people are increasingly concerned about. For decades, wastewater treatment plant sludge, the stuff left over after a wastewater treatment plant does its magic, that sludge has been rebranded as biosolids that are then applied to agricultural land to produce typically not food directly for human consumption, but for animals or for feed and forage, that kind of thing. And we know of very direct instances of PFAS contaminated sludge leading to contamination of food supplies.
Yeah, wow.
So
I mean,
I'm not sure. I don't think I answered the question exactly for the Cape Cod person in terms of what's going on with airborne emissions. I think the answer is that we don't have enough information yet. It's certainly a source of concern, especially because studies have measured airborne emissions many miles from industrial facilities. So it's certainly a concern, but I don't think there is existing data that makes epidemiologic links between airborne emissions and health outcomes yet.
And I think that question too just kind of speaks to that recent article that you just wrote, right? Like people don't really know about like PFAS in the air, and how does that kind of like spark people's curiosity to get involved in the conversation, to seek out that literature. So
Yes.
putting some research methods to work here. Okay, another anonymous person asked, tribal water systems are underrepresented in PFAS testing. Do you see any similarities with underrepresenting US territories, some of which also have high indigenous population?
Yes, absolutely. And our lab has really received feedback very helpfully from folks who have connections with U.S. territories. Several when we first launched an earlier version of our map, I'm sorry to say we didn't visualize territories on that map, and I really appreciate the feedback of folks who said, what are you doing? This, the territories need to be visually represented on our map. And so they certainly are there now. But I think it's another example of how we don't have sufficient data on PFAS contamination in the territories. And that's not an accident. There might be underrepresentation of territories in PFAS testing initiatives, partly because of the sort of unintentional design feature like we found in the tribal testing database. But we also know that this could be an area of what science and technology scholars call undone science, which is research that simply isn't conducted because it's not a priority for those in power. And understanding more about how the US state and US corporations have contaminated territories is not a priority for people who are in power and for those agencies who are in power. So we certainly hope to see more testing conducted and more information developed. Some of our collaborators are working on proposals to do exactly that, but it certainly is an area that needs a lot more attention.
Really well said. We just have a few more questions here. I don't want to bombard you with too much.
No, that's okay.
Tamala
I invited
asked,
it by not talking as long as I could have.
There you go. Yeah, we're gonna give you some hardballs.
Okay.
Can you elaborate on the 4 PFAS regulation as a group? Are the 4 together less than 1 parts per trillion? I noticed the 4 each had a limit, so I'm confused about the amounts.
Right. It is a different approach. I'm just going to go back to that slide and I'll put it up on the screen. So it is a different approach to handling PFAS than has been done before. There are several states that have something like an MCL for the sum of a certain number of chemicals, and that's not exactly what you have here in the hazard index approach. So my understanding from a quick read of the documents and from talking to folks who are at EPA or other federal agencies is that what the hazard index means is that we have these 4 compounds and they each have a level that corresponds to a hazard index of 1, which basically means if all you're talking about is, say, PFNA, and you have 10 nanograms per liter of PFNA, then you hit that hazard index level, which would trigger the MCL. But say you have some PFNA, and then you also have some Gen X. If you have a combination of PFNA and Gen X that leads to a cumulative exceedance of the one hazard index level, then you also can exceed that overall hazard index. And I picked those two because they both have 10 as their sort of hazard index equivalent level. So imagine if you had a PFNA level of 6 and a Gen X level of 5, you put those two together and you're going to be at more than a 1.0 unit hazard index. Which would trigger the MCL. PFHXS is a little bit lower. PFBS is quite a bit higher, 2,000 nanograms per liter. And there are other MCLs for PFBS that also come out quite a bit higher than these other PFAS that have been regulated through this MCL. If I didn't explain it clearly that time, I'll try it one other way, which is with the hazard index, you can imagine that for each of these 4, you take the level that's measured and turn it into a fraction over the number that's listed here. And then you add those fractions together. So if with PFNA, you end up with, in the case the example I gave, a fraction, which was 6/10, so 6/10. And with Gen X, you'd have a fraction of 5/10, which is 5/10. You'd end up with 11/10, or that would equate out to a 1.1 hazard index, which would put you over that level. So you just take each of these 4 and turn them into a fraction, add the fractions together. And if it's more than 1, then you're going to exceed that hazard index approach. The one other benefit of the hazard index approach that I have heard is that it will let EPA, at some point, if they wanted to, they could add other compounds to this hazard index, so that rather than just creating a whole separate MCL for an additional PFAS, they could put other PFAS inside this hazard index bucket, with the idea that we're thinking about PFAS more in terms of cumulative exposure, because they target the same organ systems, they lead to the same health endpoints. So we shouldn't be thinking about each of the individual PFAS health contributions as separate. We should be thinking about them as cumulative, and that's a little bit what the hazard index approach is supposed to let us do.
Yeah, I mean, some of the science goes over my head, but I think that, kind of just speaks to the importance of regulating PFAS as a class,
Yes.
rather than just trying to each individual one, right?
Yeah.
And Tamala also asked, what exactly is a 1 unit?
My understanding is that the unit is, I want to say the unit is unitless. That's not very helpful. It's just a way of saying, like, is it over the cutoff or is it under the cutoff? If the level is under a cutoff of concern, then EPA is essentially saying, we don't think this level of contamination is going to lead to harm if you consume this every day for the rest of your life. Whereas if it's over this cutoff, we think it will, we think there's a potential, and so it needs to be cleaned up before it's delivered to people in their drinking water.
Sure. Just 2 more questions here, and then we'll wrap up.
Sure.
Have salmon been tested for PFAS?
Oh, that's a great question. I'm sure there is salmon testing. I'm not thinking of any studies off the top of my head, but I can dig around and send them to Adam if I come across any.
Yeah, and I will speak on that just a little bit.
Maybe you know about this a little bit, Adam.
Sure. As far as aquatic Arctic mammals, I don't believe salmon is the top of our priority as far as what we test, but I know as far as we had another guest who was in the Canadian Arctic for our last Che Alaska, and she was talking about some of the animals that they test as far as like seals and other so I'm sure other fish would fall in that category as well, but like caribou and other subsistence foods as well. So I'm not sure. I'm sure that there's probably PFAS in salmon as well. I don't see why. And Erica, actually, somebody in our chat just said Woods Hole might have data on salmon. So yeah, I will definitely make sure that we have information on that. And actually, Sarah Howard just dropped some info as well. So if you look in the answered there, And Tamala says polar bears and seals are through the roof because of salmon. Yeah. So again, that bioaccumulation, and it kind of moves up the food chain as well. So yeah, I mean, it's all correlated, right? And we actually have a lot of resources pouring in the answered section on some PFAS testing of salmon. I'm a little bit less familiar with specific salmon, but I don't know why they wouldn't be included, just because they are such a huge source in of food in Arctic, ecosystems. One more question from Anonymous here. You mentioned artificial turf at the beginning. How much of this is contributing to PFAS in water and biosolids?
That's a great question. So I would say we don't know. However, there certainly would be concerns for PFAS being a source of groundwater, surface water and groundwater contamination, and concerns about PFAS ending up in, or concerns about turf ending up in landfills. We know that turf has a short life. It's a bunch of plastic and other stuff, and then you put it in a landfill almost always. There is virtually no sort of closed loop recycling of artificial turf at all. And the recycling claims that are made appear to be mostly greenwashing, with perhaps some very small exceptions. However, and so there has been testing of runoff from turf fields that finds measurable PFAS. And there are multiple studies that test turf samples and find PFAS in those levels. Find PFAS in the turf. However, at this point, turf fields are not sort of ubiquitously known to be sources of PFAS contamination. It is the case that PFAS are in lots of other things as well. And so PFAS are in turf, but they are also in lots of other things in our home, work, and play environments. So an area where certainly more research is needed, and there's certainly cause for concern.
Yeah, it's kind of funny. Somebody at the National CHE chapter, her name is Rachel, and we work together, and she's actually researching PFAS in turf right now as we speak, which is pretty timely. So, and I think it kind of just goes to with the more we find out about PFAS and what it's in, then we can kind of identify some of those sources. And I think that you make a really good point, Dr. Cordner, about runoff from turf too, right? Just as equally as important. And as far as firefighting foams in Alaska, we know that, it runs into the streams. We just did an independent water quality testing in February of some popular bodies of water, and we found PFAS in all the bodies of water we tested. And some of the highest were directly south of either airports or military bases. And then again, it bioaccumulates in the fish that swim in them, similar for some of these bodies of water that have triggered fish consumption advisories in Fairbanks. That's kind of just giving a little bit more context to the problem in Alaska. I do have just a few more here. I've heard reports of mercury released from thawing permafrost. Do you think PFAS is stored in permafrost?
I do not know. I think that's a great question, and I have not heard any discussion about PFAS in permafrost. PFAS are very water soluble, and so to the extent that they would make it into moisture or water, which would end up in the permafrost layer, it certainly seems plausible, but I don't know of any studies up to this point that have tested for PFAS in the permafrost.
Sure. And then Tamala just says that her school installed turf and told her that there's no PFAS in it. She said, I don't think it is third-party tested. I know it is not regulated. Could you speak on that maybe just a little bit?
Yes, so my understanding is that any claims that a turf company makes that there is no PFAS in their turf, that those claims are almost certainly misleading. That perhaps it is the case, depending on the type of turf and the type of infill that was installed, it is perhaps the case that PFAS are not intentionally added as a component of the turf, but I'm not aware of any turf samples that have been tested for PFAS where PFAS have not been detected. And so I think it is an instance of whether it is sort of inadvertent contamination during the manufacturing process, whether it is linked directly to that manufacturing process in that process of extruding the little blades of grass from the machinery, or whether it is intentionally added. I'm not aware of any turf that doesn't have PFAS, measurable PFAS. It depends, though, on how you define PFAS and how you define measurable. So if you are doing, I've seen some turf company testing data where the levels of detection are in the double-digit parts per billion. That's not a level that is sufficiently low for me to feel comfortable saying there's no PFAS there. We want to be down to the same level of detection that you would find with the sort of the EPA's methods, which is going to be around 1 part per trillion. So if you are told that there's no PFAS, and if you are given documentation that there's no PFAS, I would suggest you make sure that it says what the level of detection is, and if that level of detection is much higher than 1 part per trillion, the level of detection should not be higher than 1 part per trillion. That's the lowest, that's the smallest amount that can be detected. So make sure that the level of detection is sufficiently low, and then see how many PFAS they're testing for. If they're only testing for PFOA or PFOS, I guess it's possible that there could be a turf sample that doesn't have PFOA or PFOS in it, although I've seen multiple testing results that do have both of those compounds, actually. So again, it's sort of, how do you define PFAS? Is it just a couple, or is it the 29 on EPA's method, or is it the chemical class, like a total organic fluorine measure? And then what's the level of detection? Yeah, and I'll say maybe sort of one final takeaway point. We're talking about PFAS in turf and PFAS contaminating our food system, and all of this to me speaks to the need for a more precautionary approach to this class of chemicals, which says that in virtually every one of their uses today, perhaps with a few small exceptions, but in almost all uses, the use of PFAS is not necessary for the health and survival of our society. It might be the case that there are a small number of uses where there truly is no safer alternative, and there really is a necessity for the functioning of society or for human health or something like that for a small number of uses of PFAS. But PFAS are used in hundreds of different use categories, and most of them are most of those uses are things that offer some sort of marginal improvement in the maybe ease or sort of flow of someone's quality of life, or they make it easier for corporations to sell the things, to produce and sell the things that they're wanting to produce. So, we certainly don't need to have PFAS in dental floss and PFAS in waterproof cosmetics, and we don't need PFAS in food packaging, because we know that there are so many food packaging materials on the market already that have no detectable levels of fluorine. So it just really speaks to the need to turn off the tap of ongoing and new uses of this class of chemicals, because any PFAS emissions that take place going forward are going to be with us for decades, if not longer, and continue to negatively impact people's health and the health of the environment. So just really need to be taking a more precautionary and upstream approach to this class of chemicals.
Really, really well said, Dr. Cordner. We are going to wrap up there. Are there replacements for PFAS?
Oh, yes. So one of the things that is exciting about the work that a lot of environmental health nonprofit groups are doing, where they are testing different categories of consumer products or looking at different ways of making products. If you look at, say, food packaging, you find PFAS in some, but not all. And that says already there are alternatives that are on the market and available. We know of one interesting case in, I think it was Denmark, I guess it would be more than 5 years ago now, where a grocery store fully removed all PFAS from all of their products. And for a hot minute, there was no way to make microwave popcorn bags without PFAS. And it did not take long before the market responded with a PFAS-free microwave popcorn bag. And this is the only consumer product that at least I'm aware of where there truly was no non-fluorinated alternative. So there certainly are alternatives. It's very important that as you know, companies and retailers are making these decisions about product substitution, that the alternatives truly are evaluated and are shown to not have their own concerns for human health, environmental health, for climate change impacts. There are lots of other regrettable things that could take the place of PFAS, and so this really is also an opportunity for companies and for society more generally to switch to safer chemistry.
Yeah, really, really great stuff there. And I will just speak to the importance of, environmental justice groups and other nonprofits, NGOs that are doing the brunt of this work. You know, we've been putting pressure on retailers like REI for the last 3 years with Toxic Free Future. And they have a campaign called Mind the Store with Mike Shade. It's all great stuff. And they just committed to phasing out PFAS over the next 5 years, which is great. I think that's a really solid example. So again, Dr. Alissa Cordner from Whitman College, associate environmental sociologist, professor there teaching, and also co-director of the PFAS project lab, making sure that this research is accessible and super collaborative. I will say that this presentation has been brought to you by CHE Alaska, Collaborative Health in the Environment. It's a program of Alaska Community Action on Toxics. And CHE is a international partnership, of 5,000 individuals in 87 countries, making environmental impacts to human health accessible for everyone. We'll make sure that everybody gets a copy of this webinar with links and so many answers that we went through today. I know we had a 30-minute Q&A with Dr. Cordner, and thank you so much for being here.
Yeah, thank you all. And folks should feel free to email me or to check out our website. Thank you so much.
All right, everybody, take care. That's going to do it for us. And we hope to see you back here again on the 29th when we have Dr. Arlene Blum. Take care.